Hello everyone! Welcome to another JavaScript game tutorial. My name is Hunor, and in this tutorial we learn how to code a modern version of the 1991 classic game Gorillas. This tutorial is going to be both a JavaScript game tutorial and an introduction to the HTML canvas element. First, we learn how to draw on a canvas element with JavaScript. How to draw the background, the buildings, the gorillas, and the bomb. We don't use any images here, we draw everything in code. Then we add interaction. We add event handlers, we cover how to aim, how to animate the bomb across the sky, and how to detect if the bomb hit the enemy or a building. There are many fine details in this game. For instance, the buildings are destructible, and the hands of the gorillas are moving while we aim. I'll explain everything in as much detail as possible, especially drawing. But to get the most out of this tutorial, you need to have a basic understanding of JavaScript. Gorillas is a game from 1991. In this game, two gorillas are standing on the rooftops of randomly generated buildings and take turns in throwing explosive bananas at each other. In each round, the players set the angle and the velocity of the throw, and keep refining it till they hit the other gorilla. The flying bomb is affected by gravity and the wind. We are going to implement a modern version of this game. We are going to implement it with mouse support and nicer graphics. We also add AI logic for the enemy gorilla, so you can play against the computer, or set the game to autoplay and just watch two gorillas fight each other. In the description below you can find a link to the final extended version of the game that we are about to implement on codepen. You can give it a try before we get into it. If you are stuck, you also find the source code on GitHub for each major step. Now let's get into coding. Okay, so let's get into it. To implement this game, we are going to have a simple HTML, CSS, and JavaScript file. You can break down the JavaScript logic into multiple files if you want, but for the sake of simplicity, we have everything in one place. Because we use plain JavaScript and we don't use any libraries or third-party tools, we don't need any compilers or bundlers. We can simply run things directly in the browser. If you are coding along, to simplify the process, I recommend installing the Live Server VS Code extension. With this extension installed, you can simply right-click the HTML file and select Open with Live Server. This will run a live version of the game in the browser. This means we don't have to hit the refresh button in the browser every time we change the code. It's enough that we save the changes and the browser will refresh automatically. Now let's look into our initial files. We create three files, an HTML, a CSS, and a JavaScript file. Initially, our HTML file is very simple. In the header, we add the link to our style sheet and to our script file. Note that I'm using the defer keyword to make sure the script is only executing once the rest of the document is parsed. Otherwise, it would end up with some errors because the JavaScript file tries to access the canvas, which is not yet parsed. So now the main thing is in the body. We add a canvas element. We are going to paint on this element with JavaScript. Almost everything that will be on the screen will be painted on this canvas. Later we are going to add a few more things into this file. We add, for instance, info panels to show the angle and the velocity of the current throw. But for now, that's all we have. Initially, our CSS file is also very simple. Later we are going to add a few more things to HTML and then we will update this file. But for now, let's just make sure that our canvas can fit the whole browser window. By default, browsers tend to add a little margin or padding around the body element. So let's remove that. And finally, let's check out the JavaScript file. We are going to have a lot of things here. So before we get into the details, let's walk through the outline of this file. we define the structure and add a few placeholder functions that we are going to implement as we go. The first major building block is the game state. This is an object describing many aspects of the game. From the size of the buildings to the current position of the bomb, it includes many things. The game state includes things like whose turn it is. Are we aiming now, or is the bomb already flying across the sky? These are all variables that we need to keep track of. For now, the game state is an empty object. We are going to set it up later when we get to the new game function. Then we have references to every HTML element that we need to access from JavaScript. For now, we only have a reference to the canvas element. Once we got the canvas element, first we set its size to fit the whole browser window, and then get its drawing context. This context will be used by the draw function. Then we have a bunch of main functions. For now, let's just quickly go through what these functions do, and as we follow this tutorial, we're going to describe each and every one of them in detail. It all starts with calling the new game function. We initialize the game state and paint the initial scene by calling the new game function. This function call here is the only top-level function call in the whole code. This is where everything starts. Then the next major building block is the draw function. This function will draw almost everything you can see on the screen. It will paint the entire screen from top to bottom every time we call it. And we are going to call it many times. First, we will call it when we initialize the game. We call it from the new game function. That will paint the level for the first time. Once we could paint the initial scene, of course this is a game, so we need to make things interactive, and we add event handlers. We add event handlers to aim the bomb, and that will trigger the throw bomb function that kicks off the animation cycle that moves the bomb across the sky. The animate function will be responsible for calculating the exact position of the bomb as it moves across the sky. On top of that, it also has to figure out when this movement will stop. With every movement, we check if we hit a building or the enemy, or if the bomb got off screen. In these cases, we have to stop the animation. We add hit detection. So these are the main parts of the game. Of course, we are also going to add a few more utility functions, but they are less important, so we are going to discuss them when we get there. Now, after this quick overview, let's get into the details. Everything starts by calling the new game function. Let's check out what's happening inside of it. This function initializes and resets the game state. It generates metadata for the level and calls the draw function to draw the whole scene for the first time. First, we are going to initialize the game state. This is the state object that we declared at the very beginning of this file. Now let's see what's inside of it. Inside this object, we have several properties describing different aspects of the game. For instance, we have the background buildings array. We are going to use a utility function to initialize this array. This utility function will generate a metadata for the buildings in the background. Then the draw function will use this metadata to paint the buildings in the back of the screen. This array contains the position and the size of the buildings in the background. We also have an array that describes the main buildings. Their metadata is almost the same, except the main buildings also have windows. We need to store if the lights are on or off in each room. We generate this array in a similar way as we generate the metadata for the buildings in the back. We will cover these functions when we get to draw these buildings. Then we have an array that includes the blast holes. The main buildings are destructible, and we need to keep track of the impact positions. We will cover this later when we get to hit detection. Then we have a property that tells us whose turn it is. Player 1 is on the left and player 2 is on the right. This value works together with the game face property. This one is right at the beginning of our state object. We start the game in the aiming phase. By default, player 1 is throwing the bomb. A couple of things depend on this value. Among others, the event handlers for throwing the bomb only work if we are in the aiming phase. Then we have a wall object describing the bomb. It includes the bomb's current position, its velocity, and its rotation. Its initial position has to be aligned with the hand of the gorilla that stands on the second building, so we can only initialize this once the level is generated. We use another utility function for this. The game phase can also be in flight. In this phase, the bomb flies across the sky. We will use the animate function to move the bomb. Once we hit the enemy, the game moves on to the celebrating phase. This again affects how the draw function paints the scene and what interactions are possible. The function ends with calling the draw function. We paint the scene for the first time based on the state. If you are coding along, make sure that you have some empty placeholder functions for the utility functions that we are calling. Otherwise, you might get an error for calling undefined functions. Now we have the outline of the application. We have our initial structure. And we even initialized some of the state. But our screen is still empty. So let's get to the exciting part. Let's start drawing onto our canvas element. The draw function paints the whole canvas based on the state. We draw layer by layer. First we draw the background. We fill the background with a gradient and we add the circle that will be our moon. Then we draw the buildings. We have two kinds of buildings. We have the buildings in the background and we have the main buildings. Our gorillas are going to stand on the main buildings. The buildings in the background are simple rectangles that we draw based on our metadata. Then we draw the main buildings. These are also rectangles, but they also have windows. Then we draw the gorillas. Drawing the gorillas will be a bit more complicated as we won't just draw basic shapes anymore. We are going to draw curves and polylines. And the gorillas also have different variations based on the state. We have a throwing gorilla with one hand up holding the bomb. We have a waiting gorilla with both hands down. And we have a celebrating gorilla with both hands up and smiling. And finally, we draw the bomb. This will be a simple circle at first, but later we make it more complex. Now let's see how to draw on the canvas element. Before we get into the draw function, let's review how we access the canvas element in JavaScript, and let's see a few quick examples. At the beginning of the file, we get a reference to the canvas element in HTML. The first thing we do is set its size to fill the entire browser window. Then we get the drawing context. The drawing context is a built-in API with many methods and properties that we can use to draw on the canvas element from JavaScript. Let's see a few quick examples. The most basic thing we can do is fill a rectangle. With the fillRect method, we specify the top left coordinate of a rectangle, and then we set its width and height. By default, the fill color is going to be black. We can change it by setting the fill style property. The way Canvas works is that we have to set up the drawing parameters before we paint and not after it. It's not like we paint a rectangle and then we can change its color. Once something's on the canvas, it stays as it is. You can think of it like a real canvas, where you also pick a color with your brush before you start painting with it. Then once you painted something on the canvas, you can either cover it by painting something over it, or you can try to clear the canvas, but you can't really change existing parts. That's why we set the color here up front and not after drawing the rectangle. We are going to draw a lot of rectangles in this game. The buildings, both in the background and in the front, are simple rectangles. Even the windows on the main buildings are rectangles. We can, of course, draw more complicated shapes. We can define a path. Paths start with the begin path method and end with calling either the fill or stroke method, or both. In between the begin path method and the fill or stroke method, we build up a path by calling path building methods. This might sound a bit complicated at first, but let's just walk through this example. In this example, we move to the 300-300 coordinate with the move_to method. This will move our invisible brush to this coordinate. Then we call the line_to method to move to the right side of the shape. And then we finish this path by calling another line_to method with the 300-400 coordinate. Now, none of this would be visible on the screen if we didn't end this path by calling the fill method. The fill method will fill the path we just built up. In a very similar way, we can also draw a line. Here again, we start with the begin path method. We also build up the shape with a move_to and two line_to methods. However, in the end, we don't call the fill method, but we call the stroke method. This, instead of filling the shape, will draw the line we built. Strokes also have different styling properties. Instead of calling the fill style property, we set the color with the stroke style property. To this property and also to the fill style property, we can assign any color value that is valid in CSS. We can also change the line width to make it more visible. We set the line width property. We can also build more complex paths. Here we draw a curve. We are going to cover this in a bit more detail when we draw the arms of the gorillas. The arms of the gorillas are also going to use a curve. Now, these were just a few quick examples to give you an idea of how drawing on a canvas element works with JavaScript. Now let's get back to our game and let's look into what's inside of our draw function. When we use canvas, we have the coordinate system origin at the top left corner of the screen, and it grows to the right and downwards. This is how websites work in general. Things go from left to right and top to bottom. When we talk about a game, it's more convenient if things go from bottom to the top. Then we can think of the bottom of the screen as the ground and we can build on top of it. For instance, when we draw the buildings, we can start at the bottom and we don't have to figure out where the bottom of the screen is. We can use the translate method to shift the entire coordinate system to the bottom left corner. We move the coordinate system down along the y-axis by the size of the browser window. Once we do this, the y-coordinate is still growing downwards. We can flip it by using the scale method. Setting a negative number for the vertical direction will flip the entire coordinate system upside down. We must do this before we paint anything on the canvas, because the translate and scale methods do not actually move anything on the canvas. If we painted anything on the canvas before, they would stay as they are. Technically, these methods change the transformation matrix. You can think of it as changing the coordinate system though. Anything we paint after will be painted according to this new coordinate system. The translate methods accumulate. This means that if we call the translate method twice, the second doesn't just override the first one. It will move the coordinate system again. We are going to call the draw function multiple times in the animation loop. So we need to be sure that every time we draw, we start from the same point. We need to reset these transformations once we finish drawing. Otherwise, the coordinate system will move out of the screen to infinity. We can restore transformations by calling the restore method at the end of this function. The restore method resets transitions and many other settings to the state the canvas was before the last save method. That's why we often start a painting block by saving the context and ending by restoring it. Now that we moved our coordinate system to the bottom left corner, let's start drawing. Because we are about to draw many things, we break down drawing into multiple functions. First we draw the background. We paint the sky and we draw the moon. To paint the sky in the background, we define a gradient. We can define a linear gradient by defining its start and end point. In our case, we go from the bottom of the screen to the top of the screen. Both x-coordinates are 0 because this gradient is entirely vertical. Then we add two color stops. Where does the gradient start and where does it end? We set the top of the screen to a darker peach color and the bottom of the screen to a lighter variant. It's a very subtle gradient. The two colors are almost the same. Then we set this gradient as the fill style and we draw a rectangle. Here we set the starting point to 0, 0 and set the size of the rectangle to fill the entire window. This will be our base layer. Then we draw a moon. Drawing the moon is a bit more complicated. The moon is a simple circle, but unfortunately there's no fill circle method. There's no easy way to draw a circle on a canvas. We have to draw an arc. And unfortunately, drawing an arc is a relatively complicated thing. Let's see how we can draw a circle. We saw some of these methods at our basic examples. We draw a path. We start with the begin path method and end with the fill method. In between, we call the arc method. This can look a bit scary, but we only need to focus on the first three arguments when we are drawing a circle. The first two arguments are x and y, the standard coordinates of the arc. Here we set x to 350 and y to 300. The third argument is the radius. We set it to 60 units. Then the last two arguments are the start angle and the end angle of the arc in radians. Because here we want to have a full circle and not just an arc, we start at 0 and end at a full circle in radians, which is 2 times pi. If you don't fully understand what's going on here, don't worry about it. What's important is that when we draw a circle, the last two parameters are always 0 and 2 times pi. Before we draw the circle, we also change the fill style to a semi-transparent white. When setting the fill style property, we can set any color value that is valid in CSS. Here we use the RGBA function to be able to set also the alpha value. Now we should see a simple gradient and a circle. It's time to add some buildings. In the draw function, the next step is calling the draw background buildings function. Before we draw the buildings, first we need to set up some of the remaining metadata. In the new game function, we call the generate background buildings function in a loop. We haven't implemented this function yet. This function is meant to initialize the background buildings array in our state. Now let's look into the shape of this array. Each object in this array represents a building. Each has its own starting position and size. You might notice that we only define the x-coordinate. The y-coordinate is always going to be 0. Buildings always start at the bottom of the screen. You might also notice that the buildings are always aligned with the previous ones. There's the same gap between them. We can calculate the position of the next building by adding together the position and the width of a building and adding a gap. Buildings, of course, also have a height. Now let's see how we generate this metadata. First, we calculate the starting position. When we generate metadata for a building, we always get the index of the building as an argument. Based on this, we can look up the previous building and take its position and size. We add these together and add 4 units as a gap. If there's no previous building, then we start at the -30. This is just a random number to add some variety to the two kinds of buildings we have. The main buildings will start at 0. Then we generate the size. The width of a building is a random number within a range. We set the minimum and maximum width of a building. We can see that the buildings here are all between 60 and 110. We use math.random to generate a random number for the variable part and add the minimum width to it. We generate the random height the same way. We also pick a random height from a range between 80 and 350. The range is much bigger in this case. Then once we've finished, we push the metadata object into the background buildings array. By calling this function in a loop, we initialize another part of our state. Now that we have the metadata, we can draw the buildings on the screen. Back in the draw function, we call the draw background buildings function. This is a very simple function. We iterate over the array we just generated and draw a simple rectangle for each item. We set the fill style to a simple color value and use the fillRect method again. We call this method with the attributes of the building. The Y position is 0 because the building starts at the bottom of the screen. Once we are done with this, we should see the buildings in the background. The metadata is regenerated every time we start the game. Every time we refresh the browser window, we see a different set of buildings. Now let's draw the main buildings. For the main buildings, the same story goes again. First, we need to generate metadata in the new game function. Here we use another loop to generate metadata for the main buildings. We call the generate buildings function 8 times. Let's see what this function generates. The metadata for the main buildings is very similar to the buildings in the background. One big difference is that the main buildings have windows. They have a lights on array that defines whether the lights are on or off in a room. If the lights are on, we need to draw a window. Now let's check out this function. The generate building function starts the same way as the generate background building function. First, we calculate the starting position of a building. The only difference here is that the first building starts at 0. Then we generate the width. This again is the same as the background buildings, except we use a different range. The main buildings are a bit wider. Then we generate the height of the building. This is a bit different, because we have two cases. In case a gorilla is standing on the top of the building, then the height range is smaller. The idea here is that we want to have relatively higher buildings in between the two gorillas, so that they serve as obstacles. If we could draw a straight line between the two gorillas, then the game wouldn't be too much fun. If the buildings in between are higher though, then we are forced to throw the bomb in a curve. First we check if we are drawing a building that will have a gorilla on top. The gorillas are always standing on the same buildings. The gorilla on the left stands on the second building, and the gorilla on the right stands on the second last. If the building index matches these positions, then we set the height based on a different range. Then we generate metadata for the windows. In each room, the lights can be either on or off. To store this information, we also generate a lights on array, which stores a series of random true and false values. We generate 50 true and false values for each building. 50 is a simply big enough number. The maximum number of windows per building is less than that. We generate the booleans in a way that only a third of the rooms will have the lights on. Once we have all these values, we push them into the buildings array. With this, we generated another piece of the state. Now let's see how to use this data to draw the main buildings. In the draw function, the next step is calling the draw buildings function. Let's see how to draw the main buildings. The draw buildings function starts the same way as the draw background buildings function. We iterate over the buildings array. We set a color for the main buildings, and we draw a rectangle based on the building's metadata. Then we draw the windows. And this is the part that's going to be a bit more complicated. We have to define how we draw the windows. We define a few constants. First, we define the size of a window. We said that the window should have a width of 10 units and a height of 12 units. Now we have to decide how we arrange the windows on a building. We define a constant for the gaps. We use this constant in two places. This constant will be used to decide how far away is the first window from the top left corner of the building, both horizontally and vertically. You can think of it as the padding of the building. Then we are going to use the same constant to decide how far away the windows are from each other. Again, we are using the same gap both horizontally and vertically. From these constants and the size of the building, we can calculate how many floors do we have. We take the height of the building minus the gap above the first window and divide this number by the height of a room. The height of a room is the height of a window plus the gap. The result of this division is not going to be an integer number, so we have to round it. We round the number up with math.ceil. It's okay that the lowest floor is overflowing the bottom of the screen, because we won't see it anyway. In the same way, we calculate how many rooms we have on each floor. We take the width of the building minus the gap before the first window and divide this by the width of a room. The width of a room equals the width of a window plus the gap between the windows. This is not going to be an integer number either, but in this case we need to round this number down. Otherwise, you might end up with a window that only partially fits the building. This can result in a strange case when the windows overflow the building. While it's okay to overflow below the screen, it's not okay to overflow on the right. So that's why we have to round the number down with math.floor. From the number of floors and the number of rooms per floor, we end up with a nice grid that we can iterate over with two for loops. Now we can go through our building floor by floor and room by room. For each room, we have to check if the lights are on or off. If the lights are on, we need to draw the window. But how do we check if the lights are on? Our lights on array is one-dimensional, and our building is a two-dimensional grid. How do we map the lights on array to the building? We map the floor and room index to the index of the lights with this formula. We multiply the floor index by the number of rooms per floor and add the room index. On the first floor, the room index is 0, so we look up 0 plus 0, then 0 plus 1, then 0 plus 2, and 0 plus 3. We can see that the drawing matches the Boolean values. For the second floor, the room index is 1. So in this case, we look up 4 plus 0, 4 plus 1, and so on. This way, we can look up every room on every floor. If the value is true, we draw a window. But how can we draw the window? Positioning these windows can be tricky. Our windows align to the top left corner of the building, and the origin of our coordinate system is at the bottom left corner of the window. We could calculate the window positions in this coordinate system, but it's much easier if we translate the coordinate system again. As I said before, when we call the translate method, we do not change anything that's already on the screen. We only affect the things that we are about to paint. So we translate the origin of the coordinate system to the top left corner of the building, plus the gap horizontally and minus the gap vertically. With this translation, everything we are about to draw will use this new coordinate system. We don't exactly want that. We only want to draw the windows this way. So once we are done with drawing the windows, we restore this translation. To know what to restore, we also call the save method before applying this transformation. The windows are aligned from top to bottom. To make drawing even more convenient, we can also flip back the coordinate system. So now it goes again from top to bottom. This scaling is also restored after drawing by the restore method. With all these transformations and calculations in place, now we can finally paint the windows. We calculate the position of a window based on the floor and room index, and we draw a rectangle. With the windows in place, we covered how to draw the main building that will serve as platforms for the gorillas. So in the next step, let's check out how to draw the gorillas. Drawing the gorillas is one of the most complicated parts of building this game. It's also pretty fun. Finally, we are not just drawing rectangles. Gorillas also have different variations depending on the game state. The gorilla looks different while aiming, when they are waiting for the incoming bomb, and when they are celebrating a successful throw. In the next steps, let's see how we can draw them. In the draw function, we call the draw gorilla function twice. We draw two gorillas, one on the left and one on the right. Now that we mastered how to move the coordinate system around, we are also going to move to draw the gorillas. We translate the coordinate system to the middle of the rooftop. This makes our life easier because now we can define the coordinates of the gorillas relative to this point. It doesn't matter if we are drawing the gorilla on the left or the gorilla on the right, we can use the same coordinates. In case we are drawing the gorilla on the left, we translate it to the top of the second building. In case we draw the gorilla on the right, then we translate it to the top of the second last building. Again, this function starts with saving the current coordinate system and ends with restoring it. Then let's look into how to actually draw the gorilla. Drawing the gorilla is fairly complex, so we break it down into multiple parts. First, we draw the main part of the body. This will also include the legs and the head. We draw this as a path. In the introduction, we already talked about how to use the move to and line to methods. Here we use them to draw a polygon. First we set the fill style to black and begin a path with the begin path method. We move to a coordinate in the middle and draw a line to the left feet. Then we continue the path along the leg with another line to method. We keep adding line to methods to form a silhouette of the leg first and then the silhouette of the whole body. Once we are finished, we fill the shape with the fill method. In case you're wondering how did I came up with these coordinates, I actually started with an initial sketch with pen and paper. Then I tried to estimate the coordinates, write the code, and then kept adjusting them till they got in shape. Of course, you can have other methods as well. You can use a designer tool, and we can skip coding the drawing of the gorilla entirely and just load an image. This way, however, we have much more control. We can animate the hand of the gorilla, for instance, when we are aiming, and we can generate different variations based on the game state. Now, once we are done with the main part of the gorilla, the next thing we draw is the arms. We break this down into two separate functions. We have a function that draws the left arm and one that draws the right arm. These two functions are very similar. The left and right arm are mostly just mirroring each other. We draw the arms as a quadratic Bezier curve. The arms are actually a single curve with a relatively thick line width. In both cases, we set the line width to 18. Then we draw a path. We use the move to method to move to the starting position. This is somewhere around the shoulder of the gorilla. Then from there, we draw a quadratic curve with a quadratic curve to method. A quadratic curve is a simple curve with one control point. The curve goes from the starting point, which we set with the moveTo method, and on the way to the end point, it bends towards this control point. We set the coordinates of the control point as the first two arguments of the quadratic curve2 method. Then the curve reaches its endpoint that we set as the last two arguments. Drawing the right arm is the same, except we mirror the coordinates on the y-axis. What makes this function even more complicated is that we have three variations of the same curve. We just drew how the gorilla looks like while waiting. By default, however, the gorilla on the left is aiming. Its left hand goes up, holding the bomb. In this case, we draw a similar curve. The starting point is the same in all cases. The shoulder of the gorilla doesn't move. All the arm variations start with the same moveTo method. The only thing that changes is the coordinates of the control point and the endpoint of the curve. Deciding which variation we draw of the gorilla depends on a condition. We need to be in the aiming phase. It has to be the first player turn, and we need to be drawing the gorilla on the left. The function receives as a parameter which gorilla are we currently drawing. The gorilla on the left is player 1. The third case is when the gorilla is celebrating. In this case, both hands go up. This, of course, is only true if you are drawing the arms of the gorilla that won the game. The other gorilla is still in waiting mode. For now, the code for the celebrating case looks the same as in the aiming phase. We draw the same curve with the same arguments. We define them as separate cases though, because later we are going to make a difference. While aiming, as we drag the bomb with the mouse, the hand of the gorilla will also follow the movement. What also makes these paths different from the previous ones is that we don't end up with the fill method. We use the stroke method instead. We also set it up differently. Instead of using the fill style property, here we set the color with stroke style and give thickness to the arm with the line width property. Now let's check out if the arms look as they should. In the default state, this is how the two gorillas should look like. By default, we are in aiming phase, and the current player is the one on the left. If we change the current player property in the state to player 2, then the gorilla on the left should be waiting, and the gorilla on the right should raise its right hand. It mirrors the behavior of the gorilla on the left. If the bomb is in flight, then both gorillas are waiting, no matter whose turn it is. Finally, if we are in celebrating phase, then one of the gorillas should be celebrating, and the other one should be waiting. This again depends on the current player property. Now, if these are all good, then let's move on, finishing the gorillas. The last part of drawing the gorilla is drawing its face. This comes together from different parts. We draw the face itself, the eyes, the nose, and the mouth. We start drawing the contour of the face as an arc. This is part of a path, and we draw it the same way as we drew the moon in the sky. The first two arguments are the center position of the arc. The third one is the radius, and the last two are the same as always when we draw a circle, 0 and 2 times pi. This time, however, instead of filling the path already, we continue it. We draw 2 more circles. The 3 circles are going to be part of the same path. In between, we add a few moveTo methods to avoid a visual glitch. By default, we would end up with a continuous path, and that would look a bit off. Then once we draw these 3 circles, we fill it with the fill method. Then we change colors and draw 2 other circles for the eyes. These have the same position as the gray circles around them. Only the radius is different. Then for the nose, we draw two short lines as nostrils. They are part of the same path. We have a move to method in between to get from one side to the other. Before calling stroke, to finish this path, we set the stroke style and line width properties. These properties are also used for the next shape, the mouth. We add another path for the mouth. Technically, this could be part of the same path as the nose because we have the same line width and color, but it might be clearer to have them as separate. The mouth also comes in two variations. The fighting gorillas look grumpy. We draw another quadratic curve. This is similar to the one we had in our introduction. The start and end points of this curve are on the same level, but the control point in between is higher, so the middle of the mouth is higher than the two sides. In case the gorilla is celebrating, we draw a different mouth. The winner is smiling. The curve starts and ends higher and bends the other way. Now let's check out if this works as well, now with the final look of the gorillas. By default, the gorilla on the left is aiming. Both gorillas look grumpy. If we switch to celebrating phase, then the gorilla on the left is smiling. Look how happy it is. And if we are switching players, then the other one is smiling. Everything is good. Now that we drew the gorillas, we got one of the hardest parts of this game covered. Give yourself a tap on the shoulders, drink some water, and hey, click the like button and subscribe. If you got this far, it can be a coincidence. We are going to return to the gorillas one more time when we move the arms while aiming. But for now, let's move on with the one thing that's still missing from the screen, the bomb. Let's draw the bomb. This is the final piece of the draw function. Before we get to it though, first we need to initialize its position. If we look back at our new game function, we see that the state of the bomb's position is still undefined. The function also ends with calling the initialize bomb position before drawing the scene. Let's implement this function. The initialize bomb position places the bomb in the hand of the gorilla that throws the bomb. We have to call this function after we generate our building metadata because the bomb's position depends on the position of the gorilla, and that depends on the building it stands on. First we look up which building we need to align with. If it's the first player's turn, then the bomb has to be in the left hand of the gorilla on the second building. First we calculate the midpoint of the rooftop. Then offset this position to match the left hand of the gorilla. This will be the position of the bomb. In case it's the second player's turn, we need to select the second last building. Again, we calculate the midpoint of the rooftop, then offset this value to match the right hand of the gorilla. We also initialize the velocity here. Later we are going to call this function at the beginning of every turn, and we need to initialize these values. Now that we know the bomb's position, let's draw it. We translate the coordinate system again and move the origin to the center of the bomb's position. This doesn't matter much for now, but later we are going to extend this function and draw some other things. Then it will come handy that our coordinate system is centered around the bomb. Then, for now, let's draw the bomb as a simple circle. We use the arc method again to draw this circle, the same way we drew the moon or the circles on the face of the gorilla. Because we just moved the origin of the coordinate system to the center of the bomb's coordinate is 0, 0. Then we add the radius and the usual parameters that we use to draw a circle. Now we have everything on the screen. We drew the background, the buildings, the gorillas, and a simple version of the bomb. You might notice though that our city is not aligned to the right side of the screen. So far we aligned everything to the left side. Because the size of the buildings is random, the city might be shorter or wider than the size of the browser window. It can even happen that we don't even see the second gorilla because it's entirely off screen. Or the browser is too wide and we have a huge gap on the right side of the window, like in this case. To fix this, we are going to scale the view to the width of the browser window. Let's do this. If you go back to the new game function, you might notice that we skipped a few things. First, let's add a scale property to our state. The value of this property depends on the size of the generated buildings. So after we generate the city, let's call another function to calculate the scale. This function also has to come before we initialize the bump position because later that will depend on the scale. The calculate scale function is relatively simple. First, we calculate the total width of the city. Take the last building's position and add its width. Then take the inner width of the browser window and divide it by this number. This will give us a ratio. It will tell how the width of the city relates to the width of the window. Then we have to use this new scale property at a few places. The most important is to change the scaling of the entire game in the draw function. At the beginning of this function, where we flipped the coordinate system, now we have another scale method that applies this scaling. Because this is at the beginning of the draw function, everything we draw after will be scaled. With this, we are almost finished. This works well if we need to scale the view up. But what happens if we need to scale the view down? If the window is too narrow and we need to shrink down our scene, then we have an issue. The background will shrink too much. This is because we use the window's inner width and inner height properties to figure out the size of the background. But these properties simply give back a number, and with scaling, these numbers also scale up or down. Whenever we use inner width or inner height properties, we need to adjust them by our scaling factor. So let's fix this in the draw background function. Now the 8 buildings fit nicely with the size of the screen. But what happens if we resize the window? We are going to have the same problem we had earlier. As a finishing touch, let's handle the window resize event. This event handler does a few things. First, we resize the canvas element to fit the new size. Then we recalculate the scaling and readjust the position of the bump. Readjusting the bump position does not make any difference yet, but later an updated version of the initialize bump position function will rely on scaling. Finally, we redraw the wall canvas according to our new scaling. With all this done, we have an initial paint of the game. However, everything is still static. And of course, this is a game, so let's make things interactive. Alright, we have a static image. It's time to make our game interactive. Let's talk about how aiming works and what we need to change. In the next steps, we add event handlers to aim. We add 2 info panels to show the angle and the velocity. As we are aiming, these values will change as we drag the mouse. We also adjust the drawing of the hand of the gorilla to follow the drag movement. And we draw the throwing trajectory. These are the dots showing where the bomb will go. Before we get into event handling, first let's add these 2 info panels. These are going to be simple HTML elements in the top left and top right corner. They show the angle and the velocity while we aim, and also as a reference for the next round. We start with these because as we get into event handling, we change a lot of code, and first we won't see a lot of change on the screen. One of the easiest ways to add some quick feedback loop to see that things are actually working is to update these fields as we drag the bomb. So let's look into these info panels. We add these fields as simple HTML elements. So let's go back to our HTML file and add 2 divs. In each, we add a header with the player number, and we add two paragraphs, one for the angle and one for the velocity. Note that these info panels are after the canvas element in HTML. Otherwise, the canvas would cover them and we wouldn't see any of the infos. We could draw these text fields on the canvas as well, but it might be easier to use plain old HTML and CSS. Then we set some styling with CSS. We add some basic styling to the text fields and move the panels into position. Note that I'm setting the user select to none. This makes sure that you cannot select the text on the screen. This helps us to avoid a glitch later. Normally, when we drag the bomb, we could accidentally end up selecting the text on the screen. We don't want that, so we set user select to none. The rest of the styling is mainly just using absolute position and moving the panels in the top left and top right corners. Also note that we set class names to these fields. We will access these fields in JavaScript by class name. We will update these fields as we drag, so let's see how to access these fields in JavaScript. In our JavaScript file, somewhere at the beginning, where we also create a reference to the canvas element, let's add a few more statements. This time, because the fields don't have a unique ID, we use query selector. We access them by a query that will use both the ID of the panel and the class name of the field. For now, let's just leave the info panels like that. When we get to event handling, we will update these values. Before we get to event handling, there's one last thing. We are going to set up event handlers to drag the bomb. But what can we even drag? The whole canvas is one single element. We could attach an event handler to it, but then we could start dragging the bomb by clicking anywhere on the screen. We only want to start aiming when we drag the bomb. To solve this, we get back to HTML and add another element that will serve as the grab area. The whole purpose of this element will be that we have something we can attach an event handler to. So in HTML, we add another bomb grab area element. This won't include the bomb itself that we see on the screen, that's already part of the canvas. It will be an invisible area on top of it, serving as an event target. We add some styling to it with CSS. We make it invisible by setting a transparent background color. To give a visual clue to the player that something is going on there, we change the mouse cursor to grab. So when the mouse is over this area, it will switch to a grab icon. We set a reasonable size. Because this element is invisible, we can make it slightly bigger than the bomb in the canvas. This way, it's easier to grab it with the mouse. We also set it to be absolutely positioned. The exact position depends on the level, so we can only set it in JavaScript. So let's go back to JavaScript and look into how to position this element. First, we get a reference to it somewhere at the beginning of the file. Then we need to move it to the correct position. We already have a function that initializes the bomb position on the canvas. We extend the initialize bomb position function to position this HTML element as well. We move the grab area to the same place as the bomb, but its coordinates are a bit different. The content of the canvas is scaled, but any element outside of it is not. We need to adjust the coordinates by the scaling. Also note that we set the grab area radius variable to be half of the size what we defined for this element in CSS. This one, however, doesn't scale. No matter how big or small the bomb appears on the screen, the draggable area stays the same size. Once we added this, we won't see much difference on the screen because this item is invisible. But once we hover over the bomb, we will see that the cursor changes to grab. If something goes wrong, you can also change the background color to something non-transparent, so you can see where it is. Now with this in place, we can finally add the event handlers. This is going to be a simple drag and drop implementation. We listen to the mouse down, mouse move, and mouse up events. Note that we are using the grab area element only for the mouse down event. For mouse move and mouse up, our event target is the window. This is because we want to start the dragging movement with the mouse being over the bump, but as we are dragging, we can move the mouse outside the grab area and we still want the event handlers to work. Now let's look into these event handlers. First, we set up some top-level variables somewhere at the beginning of the file. We have a variable that tells us if we are currently dragging or not, and two variables that tells us where did the drag start, in case we are dragging. We add the first event handler for the mouse down event. Being able to set this event handler is the whole reason we added the bump grab area element earlier. This event handler only does anything in case we are in the aiming phase. In any other case, we simply ignore it. If we are in the aiming phase though, then first set the isDragging variable to true. Then save the current position of the mouse and set the mouse cursor permanently to grabbing, so that the cursor stays as grabbing even if we leave the grab area. Then we add an event handler for the mouse move event. Note that now the event target is not the grab area of the bump, but the window object. This event handler checks if we are currently dragging. If not, then it doesn't do anything. If we are dragging, then it calculates the delta of the mouse position since the mouse down event and sets it as the velocity of the bump. As we are aiming, we drag the mouse backwards, just like we are aiming in Angry Birds and other games. But of course, the bump will move forward after we release the mouse. So we assigned the horizontal and vertical mouse movement with a negative sign as the velocity. But with a double twist, we switch back the vertical velocity, the y-coordinate, to have a positive sign because we flipped the coordinate system. Event handlers still assume that the coordinate system grows downwards, and within the canvas, it's actually the opposite. Then we update the info panels we added earlier in HTML. We call a utility function to show the angle and the velocity. We have a separate utility function for this because from the event handlers, we only get the horizontal and vertical components of the velocity. We need to transform these values. We can do this with some basic trigonometry. In a right-angled triangle, we can calculate the length of the hypotenuse by adding together the squares of the two other sides and taking the square root of that. In our case, if we add together the squares of delta x and delta y, then take the square root of the sum, then we get the velocity. We can also calculate the angle by dividing the length of the opposite side by the hypotenuse and taking the inverse sign of that. In our case, if we divide delta y by the velocity and take the inverse sign of that, then we have the angle. We start the setInfo function by these calculations. JavaScript's built-in arcSine function works with radians though, so we have to convert the angle from radians to degrees. Then we update the content of the appropriate fields, depending on the current player. In the previous step, we already added references to these HTML elements, so here we can simply set their inner text property. We also round these numbers to make sure they look good on the screen. Then after setting the info panels, back in the event handler, we also call the draw function. For now, calling the draw function here doesn't do anything. But soon we will update the code that draws the hand of the gorilla to follow the drag movement. Then we will need the draw function to repaint the scene with every little drag movement. At this point, while the hand does not follow the movement yet, if we start dragging, the values in the left info panel should update as we drag. Finally, we add the event handler for the mouse up event, again on the window object. This one stops the aiming by setting the isDragging variable back to false. It changes the cursor back to default and calls the throwBump function. The throwBump function will eventually kick off the animation cycle. We are going to cover this function in the next chapter, but before we get there, let's do a few fine-tunings. So far, while we are dragging the bump actually stays in the same place. We only see that something changed in the info panels. It would be much nicer if the bump, together with the hand of the gorilla, would follow the drag movement while we are aiming. Let's do that. This is where we left off drawing the hands of the gorillas. We had 3 different cases for the 3 different game phases. And you might remember that we had the same values for the arms, for the aiming, and the celebrating phase. It's time to make these 2 cases different. The last 2 values of the quadratic curve2 method set the endpoint of a curve. We are going to adjust this point in the opposite direction of the velocity. The velocity points forward, but the mouse movement pulls the bump backwards. We don't exactly follow the mouse movement. That would end up with unrealistically long or twisted gorilla arms. We only move the hand in the direction of the mouse movement. We divide the velocity values by a constant. We make the same adjustment for both hands. Note that while so far the coordinates of the left and right arms always mirrored each other, now this adjustment is the same. In both cases, we subtract these values. Now as we are aiming, the hand of the gorilla follows the drag movement, but the bump is still left behind. Let's update the function that draws the bump. This is where we left off the drawBump function. Let's add another translation in case we are aiming. This translate command moves the center of the coordinate system along with the hand of the gorilla. We use the same shift with the same constant to match the hand of the gorilla. Now both the bump and the hand of the gorilla follow the drag movement. While we are aiming, we can also draw the throwing trajectory. This will show in a visualized way the velocity and the angle. To do this, let's go back again to the drawBump function, and let's add a couple more things. In case we are in the aiming phase, we draw a straight line from the center of the bump to the velocity. We draw this line as a simple path. The path starts with the begin_path method and ends with the stroke method. In between, we add a move_to and a line_to method. Because we moved the origin of the coordinate system to the center of the bump, the start of this line is at 0, 0. The end of the line matches the horizontal and vertical component of the velocity. There's one new thing here, the setLine_ method. With this setting, we can draw a dotted line. We set that after every 3 pixels of line, we want to have 8 pixels of gap. The 3 pixel dash matches the line width, so the dashes look like dots. Because the translate methods are before this stroke, when we move the bump, this trajectory will also move together with the bump. Now we finished everything about the aiming phase. It's time to throw the bump. After aiming, once we release the mouse, the bump flies across the sky. We add an animation loop that moves the bump. It calculates its position with every animation cycle, and it checks if we hit something. We also animate the bump itself. When the bump is in flight, instead of displaying a simple circle, we animate a spinning banana. Let's see how these work. Earlier we saw that the event handler of the mouse up event ends with calling the throwBump function. Let's check out this function. This function first kicks off the in-flight phase. This is the phase when the bump is flying across the sky. Then it starts the animation loop by calling requestAnimationFrame with the animate function as an argument. The animate function will handle one frame of the animation loop. In each frame, we move the bomb by a little. Then at the very end of this function, it keeps on requesting another animation frame. This way, we end up running the animate function around 60 times every second. The constant repainting on the screen will appear as a continuous animation. The only way to stop this animation loop is by returning early from this function. Returning before we reach the last statement that requests another animation frame will eventually stop this loop. There are two cases when we stop. One is when we miss the target, when we hit a building or the bomb got off screen. In this case, we switch players, and then the next player can start aiming again. The other case is when we hit the enemy. In this case, the game ends. We will cover these cases a bit later when we get to hit detection. First, let's check out how to move the bomb as it flies across the sky. Two very important things are happening in every animation cycle. We move the bomb and we redraw the scene with the new bomb position. Moving the bomb, however, is time sensitive. Normally, a function invoked with requestAnimationFrame is called roughly in 16 milliseconds. However, slight deviation might occur, and the refresh rate can also depend on the refresh rate of your computer screen. To have more control, we can use the timestamp attribute the function receives. Functions invoked with the requestAnimationFrame function receive the current timestamp as an attribute. We can use this attribute to calculate how much time passed between two cycles. Before moving the bomb, we calculate the elapsed time by subtracting the previous timestamp from the current one. But how do we know the previous timestamp? We assign the current timestamp at the end of the function to the previous animation timestamp variable, which will eventually become the previous timestamp in the next cycle. The first cycle is an exception because at that point we don't have a previous cycle yet. Initially, the value of previous animation timestamp is undefined. We make sure it's undefined in the throwBomb function. In this case, we skip a render and we only render the scene on the second cycle, where we already have all the values we need. This is the part at the very beginning of the animate function. In this if block, we save the timestamp for the next animation cycle and we request another animation frame. Now that we have an animation loop and we calculated the elapsed time since the previous cycle, it's time to move the bomb. Let's look into the moveBomb function. This function moves the bomb by manipulating its x and y coordinates. The new x and y values are calculated based on the velocity. However, the vertical and horizontal velocity can be a relatively high number. We don't want the bomb to fly across the sky with lightning speed, so we have to slow it down. We multiply the values by a very small number. This multiplier takes into consideration how much time has passed between the cycles, so the animation will look consistent even if the animation cycles are not triggered at equal pace. With every animation cycle, the velocity of the bomb is also adjusted by gravity. We gradually increase the motion of the bomb towards the ground. We adjust the vertical velocity by a small constant that also depends on the time passed. With the moveBomb function, we move the bomb. Then later in the animate function, we redraw the whole scene with the draw function. With this, we have an animation. But so far, nothing stops the movement. The bomb moves to infinity. So as a next step, let's add the most basic hit detection we can do, detecting if the bomb hit the edge of the screen. Checking if we hit the edge of the screen with the bomb is very simple. In the animate function, we already have the outline of our hit detection. We have two variables. We got a miss if we hit a building or the bomb got off screen. And we have a hit when we hit the enemy. For now, both of these variables are simply set to false, because we did not implement the hit detection yet. Let's change the value of miss. We call the check frame hit function. This is a very simple function. We check if the bomb got out of the screen by checking if it got out of the bottom of the screen or on the left or right side. If any of these are true, then we return true from this function. This means we missed the target. If the bomb got out of the screen through the top of the screen, that's okay. Gravity will eventually pull it back. And eventually it will either reappear on the screen or it will hit one of the other sides. When we return true from this function, we have to handle missing the target in the animate function. What happens in this case? If we miss the target, then we switch players. We change the current player from player 1 to 2 or the other way around. Then we set the game phase back to aiming and reinitialize the bomb position to the hand of the next player. We redraw the scene to make it visible that we switch players, and we return from the function to stop the animation loop. Now we stop the animation loop, but we are back in the aiming phase, so the event handlers are active again. We can start throwing the bomb back and forth. Our game still doesn't make much sense because we still don't detect if we hit an enemy or a building. But we are getting there. Before adding proper hit detection, let's change the look of the bomb. In the original game, the bomb wasn't a simple circle, it was a spinning banana. Let's update the draw bomb function. This is where we left off the draw bomb function. It draws a simple circle, and in case we are aiming, it follows the movement, and we also draw the throwing trajectory. Let's restructure this function a bit. We will break down this function into 3 different cases depending on the phase. The aiming phase is the same as we had before. We move the logic drawing the circle inside the if block, but we draw the circle the same way as before. In the third case, when we draw the bomb in the celebrating case, we also draw a circle. This is again the same logic as before, but now we don't translate the coordinate system with the velocity, and we don't draw the throwing trajectory. Now the in-flight case, that's going to be a bit different. The in-flight case is when the bomb is flying across the sky. In this case, we will draw 2 curves. We draw this banana shape as a path, so we started with the begin path method. We move to the -8, -2 coordinate, and then draw a curve from there to the +8, -2. Then with another curve, we move back to the starting position. We end the path with the fill method. What's cool about positioning the coordinate system origin to the center of the bomb is that now all these coordinates can be relative to that. There's another thing that's new here. We apply a rotation before we draw this shape. We rotate the bomb by the bomb's rotation. But what's that? We haven't really covered it before. At the very beginning, when we initialized the state, the bomb already had a rotation property. It was initially set to 0, and we haven't touched it since. Let's update a few functions to make sure it behaves properly. We need to update the initialize bomb position function and the move bomb function. In the initialize bomb position, after resetting the velocity, we can also reset the rotation. And what's more important, that in the move bomb function, we are going to animate this property. Just as we move the position of the bomb, we also change its rotation. The rotation depends on which player is throwing. If the player on the left throws, then we rotate the bomb clockwise. And if the player on the right throws, then we rotate the bomb counterclockwise. Now in the drawBump function, we made sure to use this rotation that the moveBump function animates. So we have a nicer animation. Our game is still quite dull because we don't have proper heat detection. So let's add heat detection for our buildings. We add heat detection for the buildings in multiple steps. First we add the basic one, and then we will improve it. In the animate function, we extend our heat detection by also calling the checkBuildingHeat function. If this function returns true, that also means that we missed the target. This function, for now, is very simple. We iterate over the buildings array, and we check if the bump is touching one of them. More precisely, we check if the right side of the bump is on the right side of the left side of the building, and the left side of the bump is on the left side of the right side of the building, and the bottom of the bump is below the top of the building. If these are all true, then the bump hit the building. In this case, we save the point of impact into the blast holes array. We are going to use this array in the next step to display the blast holes in the buildings. If we get a hit, the function ends by returning true. This will signal to the animate function that we can stop the animation loop, and it's time for the next player. Now the game is a bit more fun. Finally, the bumps don't just magically fly through the buildings, but they actually stop when they hit one of them. But they don't seem to cause any damage to the buildings so far. So in the next step, let's draw the blast holes. The buildings are destructible. Once a bump hits a building, it should leave a blast hole behind. In the next step, let's see how we can do that. We use a clipping mask. With a clipping mask, we define an area of the screen that we can draw on, and everything else outside of it will be ignored. Let's take this example with this gorilla shape on the right here. A typical use case for a clipping mask is to define a frame for an otherwise rectangular image and cut the edges of the image with this shape. If we apply this gorilla shape as a clipping mask for our entire screen, then we would end up with something like this. Here we need an inverse clipping mask. Instead of defining where we can draw, we need to define where we shouldn't draw. We need to define the holes in the buildings. Unfortunately, inverse clipping masks are not a thing. So instead, we need to define something slightly more complicated. We need to define a mask that fills the whole screen and has some holes in it. If we apply this mask, and we apply it only for the main buildings, then we end up with the effect we wanted to achieve. But what if we have multiple holes? The cleanest way we can do is that we create multiple clipping masks. We create one for each blast hole. Then we can clip a clipping mask with another clipping mask. And with the result, we can clip the main buildings. Now let's see how we can apply clipping in Canvas. The way clipping works in Canvas is that first we define the clipping mask, then we call the clip method, and everything we draw after will be clipped. Of course, we don't want to clip everything after calling the clip method, we only want to clip the main buildings. So once we draw the main buildings, we call restore to stop the effects of the clip method. And of course, we start the whole thing by calling the save method, so the restore method knows what to restore. Now that's all great, but how do we draw a shape with a hole in it? That's something that's not very obvious. There's a rule here. The rule here is that when we draw the outer shape, we draw it clockwise. And when we draw the hole in it, in this case the circle, we draw it counterclockwise. Or the other way around. What's important is that we draw the outer and inner shapes in the opposite direction. Now with all this introduction, let's look into how to clip the main buildings. We create a new function called drawBuildings with blast holes. In this one, we will reuse the old drawBuildings function. The old draw buildings function is still perfectly fine for drawing the buildings, we just need to set up the clippings first. Now let's see how this new function works. We already collected the center coordinates of the blast holes in the check buildings hit function on impact. We iterate over the blast holes array and draw a clipping mask for each. We use the rect method to draw a rectangle. This method should not be confused with the fill rect method. The fill rect method fills a rectangle on its own. The rect method, on the other hand, is part of a path. This method doesn't have a direction, but it behaves as if we were drawing the rectangle clockwise. Once we have the outer shape, we draw the holes as an arc. By default, the arc method also draws the arc clockwise. But we can add a sixth attribute to the already complicated list of attributes to make it counterclockwise. The sixth attribute is a Boolean value, and if we set it to true, then we will draw the arc in the opposite direction. To draw the holes, we introduce a new top-level variable, blast hole radius. This variable will be used in one other place as well in the code. That's why we have it in the top level. You might notice that we start this clipping path the usual way with the begin path method, but we do not end it with fill or stroke. We do not want to show this clipping mask on the screen. We only want to clip with it, so we end it with calling the clip method. As a result, everything we draw after will be clipped, even the next clipping mask we are going to generate with this loop. Once we generated all the clipping masks and we applied the clip method, we can call the original draw buildings function. As a final step to finish up drawing the blast holes, we have to replace the original draw buildings function in the draw function with the new draw buildings with blast holes function. Once we are done with this, we can check out if it works. If we hit a building with a bomb, it should leave a blast hole behind. And it should even work if we hit multiple buildings or we hit the same building multiple times. If you play the game for a while, you might notice sometimes there's a glitch. Sometimes the bomb flies over the corner of a building without hitting it. Let's look into that. While we already slowed down the movement of the bomb can be still a bit too fast for hit detection. When the bomb is in flight, it can move by more than 10 pixels at a time. If we do hit detection only once per animation cycle, that means that we are completely blind what happens during these 10 pixel movements. The bomb can easily go through the corner of a building without the hit detection noticing it. Let's fix this problem. To solve this, we are not only going to do hit detection once per animation cycle, but we do it multiple times. We break down every movement into smaller segments, and with every tiny movement, we check if we have a hit. We still render the scene once per animation cycle, but before calling the draw function, we break down the movement into segments with a loop. Let's see how this looks in the code. On the left side of the screen, you can see the animate function as we had it before, and on the right side, the new version. We move the entire movement and hit detection logic into a new loop. We create a new constant that defines how many segments we break down each animation frame. Then we use this constant in the loop. If we break down each animation cycle into 10 segments, that also means that now we are calling the moveBump function 10 times in every animation cycle. This will move the bomb 10 times faster. To move the bomb at the same speed as before, we need to slow it down again. Because this function moves the bomb according to the time passed, it's enough if we define this time attribute also by 10. This way, the bomb moves across the sky with the same speed as before, but we have 10 times more precision with hit detection. Now we can detect if we got a hit with every pixel movement. There is another thing that we need to improve about hit detection. Now that we have blast holes, we have another case to handle. What happens if we hit a building at the same spot again? Our hit detection detects that we have a hit because we hit the edge of the original building. It does not consider the blast holes. Ideally, the bombs would keep on moving and create another blast hole within the blast hole. So let's refine the hit detection of the buildings. We should only say that we hit the building if the bomb is within the rectangle of the building, but we should exclude the already existing holes that the previous bombs left behind. To do this, we update the check buildings hit function. We keep the original parts of the function and extend it with a loop. First, we detect that the bomb is within the boundary of the building, based on the previous implementation we had before. If that is the case, we iterate over the blast hole metadata and get the distance of the bomb from the center of each blast hole. To calculate the distance between 2 points, we use trigonometry again. If it turns out that the bomb is within a blast hole, the distance is less than the blast hole radius, then we did not actually hit the building. In this case, we return false, signaling that we did not hit the building, at least not yet. If we try out our game now, we can potentially cut through a building by hitting at the same spot multiple times. Now that we have a proper hit detection for the buildings, and we even made our buildings destructible, it's time to detect if we hit the enemy. We are going to have a different approach this time. Detecting if we got a hit with traditional geometry calculations would be much more complicated because the gorillas are not just basic shapes. Luckily, in Canvas, there's a method that checks if a point is within a path. We use the isPointInPath method. This method tells us if a point is within the current or the previous path. So before calling the method, we need to recreate the gorilla. The gorilla is not one single path, so we need to test against the most relevant part, the body of the gorilla. Conveniently, and with some smart planning, we already have a function that paints the body of the gorilla as a single path. We call the drawGorillaBody function right before isPointInPath. Of course, things are not that simple. The drawGorillaBody function paints the coordinates relative to the rooftop of a building, so before calling it, we need to translate the coordinate system. Depending on the current player, we calculate which building the enemy stands on and translate the coordinate system to the top of that building. Because of this translation, we also need to use the save and restore commands. This way, we can tell if a bomb is within the main part of the gorilla. The gorilla, however, is not just the main body, it also has arms. Similarly, we can also detect if we hit the arms. The arms are drawn as a stroke, so in this case, instead of calling isPointInPath, we use isPointInStroke method. This detection would not work if we did not increase the hit detection precision earlier, because the bomb would easily go through the arm. But because we improved the hit detection precision to work in every pixel, we can also detect if we hit the arm. If we hit the main body of the gorilla, or one of the arms, the function returns true, signaling that we hit the enemy. So what do we do then? Back in the animate function, let's fill the remaining part. First of all, let's make sure to use this function. We assign the hit variable to this new function. Then in case we hit the enemy, we switch to celebrating phase and redraw the whole scene. This should redraw the winning gorilla with both hands up and smiling. We can also call a new function to announce the winner. Let's cover that in the next step. Once we hit the enemy, we should announce the winner. And we should also have the option to play another game. For this, we add a new container in HTML that will include who won the game and the reset button. So let's get back to our HTML file and add a new congratulations panel. This panel is hidden by default and it only shows up when we end the game. When it shows up, it should be in the middle of the screen. We add display flex to the body element with a few more properties to center everything on the screen. Then we set position absolute for the congratulations element and hide it by default. Then we can use this panel to announce the winner once the game ends in JavaScript. Before doing so, we need some references to the panel itself and the winner field. So somewhere at the beginning of the file, let's set up a few new references for the congratulations panel and the winner field. Then we can write the announceWinner function. We set the content of the winner field to the current player and show the congratulations panel. With this piece, we finally can play the game till the end. We can aim, the bomb flies across the sky, and the gorillas take turn until one of them wins the game. The only missing piece is resetting the game and playing another round. We set up most pieces for this already. We already have a new game button that shows up when the game is finished. In JavaScript, let's add a reference to this element, and let's add an event handler. This event handler simply calls the newGame function. The newGame function was always meant to be for two reasons: to initialize the game and to reset it. It resets the game state and generates a new level, so we can start a new game. At this point, however, the newGame function does not reset everything. It does not reset the HTML elements we introduced in the meanwhile. So let's make sure that the congratulations element is hidden once we start a new game, and we reset the angle and the velocity values in the info panels. With this, we have a full two-player game. In the next step, we check how to add AI logic so that you can play against the computer. We have an initial version of the game, but we can only play it if we have two players. Both gorillas are controlled manually. Let's add support for single-player mode. We need to program the computer-controlled opponent's behavior. Once we got this, we can even make two computer-controlled gorillas fight each other. If you think about how exactly you pick the angle and the velocity when you're aiming, you realize it's not an obvious thing. We consider the altitude difference between the gorillas, the distance, the buildings in between, and the result of the previous throws. It would be really hard to simulate this with code. Instead of that, we implement the logic with brute force. At each turn, when the computer is throwing, before it actually throws the bomb, it will run multiple simulations. It tries different angles and different velocities. It picks different values for these within a range. For each simulation, we check where does the throw end. Then we calculate the distance of the impact from the enemy gorilla. And at the end of each simulation, we check if we got closer to the enemy than with the previous simulations. We pick the best one, and that's going to be the real throw of the computer. We do not see these simulations because we do not draw them on the screen. We introduce simulation mode. In simulation mode, we will use a modified version of the existing animate function to simulate moving the bomb in the sky and to do all the hit detection for us without calling the draw function. Now let's check out how to realize this in code. We add a new function named runSimulations. The runSimulations function picks the best shot out of a number of simulations. At the beginning of this function, we initialize the best throw object. This object will contain the horizontal and vertical velocity that we return of this function as the real throw. This object also contains a distance property that we initialize as infinity. With each simulation, we check if we got closer to the enemy, and if so, then we pick that simulation as the best throw. Then we turn on simulation mode. Later, this Boolean value will impact how the animation loop works. It will turn off redrawing the scene with every cycle and make the wall throw instant. Then we calculate the position of the enemy gorilla. We will use this as a reference for calculating the distance from the impact to the gorilla. Based on the current player, we pick the enemy building and calculate the coordinates of its rooftop. Then we shift this value by half the size of the gorilla to get the center of the gorilla. Then we have a loop that runs a number of simulations. In each cycle, we pick a random angle and velocity. Not entirely random, we use sensible ranges. The angle can go between 0 and 90 degrees, and the total velocity can go between 40 and 140. To simulate the throw, we need to transform this angle and velocity into horizontal and vertical velocity components. We use trigonometry again to break down the total velocity into horizontal and vertical components. We use the cosine function to get the horizontal part and the sine function to get the vertical part. In JavaScript, these functions expect the angle in radians, so before this, we also need to convert the angle from degrees to radians. When we get to the horizontal component of the velocity, its direction also depends on the player. Player 1 throws to the right and player 2 throws to the left. We multiply the horizontal velocity by +1 or -1 depending on the player. With these values, we run a simulation. We reset the bomb position and set its velocity. We need to reset the position because the previous simulation might have moved it. Then to simulate throwing the bomb, we call the throwBomb function. This is the same throwBomb function that we used before. This time, however, we are in simulation mode. We don't want to repaint the scene as the bomb moves across the sky. Instead, we need an instant calculation that tells us where the bomb ends up. We need to modify the throwBomb function and the animate function accordingly. This is where we left off the throwBomb function the last time. It kicks off the in-flight phase, resets the previous animation cycle's timestamp, and requests an animation frame. We change it to have two separate cases. Both end up triggering the animation function, but in different ways. In simulation mode, we don't wait for the animation frame. We run the animate function instantly. We simply run the function itself. What was an asynchronous call before is a synchronous call in this case. To simulate the real behavior, we pass on a timestamp that will roughly match the time difference between two real calls. When we call this function with request animation frame, the function is called around 60 times every second. That roughly equals every 16 milliseconds. We also reset the previous timestamp to 0 instead of undefined. So the first time we call the animate function, we can already calculate the simulated elapsed time. And finally, in simulation mode, we do not switch to in-flight phase. We are still aiming. We want to draw the aiming gorilla once we are done with the simulations. Then let's check out what do we need to change in the animate function. The outline of the function is the same, but we have three parts where the behavior is different in simulation mode. The first difference is similar to what we did in the throwBomb function. At the end of the animation cycle, instead of requesting another animation frame, we call the animate function directly. We simulate the time passing by increasing the timestamp by 16 milliseconds. With this, we made the entire simulation synchronous. We can analyze the result of the simulation in the run simulations functions right after we called the throw bomb function. The second difference is right above this part. We don't redraw the scene in simulation mode. We only redraw the scene if we are not in simulation mode. The third and most important change is that once we hit a building, or an enemy, or the bomb got off screen, we quit the simulation and save the position of the impact. We quit the simulation by returning early from this function. This return statement not only prevents the animation from continuing, but also ignores the default handling of the hit detection. Before returning, we save the position of the impact in the simulation impact variable. This is another top-level variable that we are going to use back in the run simulations function to check how close we got to the enemy. Now let's go back to the run simulations function. Now that the simulation loop ended, we got back to the run simulations function. This time, because we did not use request animation frame, the wall throw simulation was synchronous. So right after we called the throw bomb function, the simulation impact object is already filled with the impact position. For each simulation, we calculate the distance between the impact and the enemy gorilla's position. We use trigonometry again to calculate the distance between these 2 points. If the impact got closer to the enemy than the previous simulations, then we pick the current simulation as the best one. Here we save the initial horizontal and vertical velocities of the throw along with the distance of the impact. We do not save the position of the impact, we only need to know how the throw started. Once we are done with the simulations, we turn off the simulation mode and return with the horizontal and vertical velocity of the best throw. But where do we even call this function? We create another function that will simulate the entire flow of the computer throw. The computer throw function has 2 parts. First, it runs a number of simulations and picks the best throw. And then in the second part, it triggers the throw itself. To make it look like the computer gets better with every turn and gets closer to the enemy, we simply increase the number of simulations each turn. First, the computer starts with 5 simulations, and we pick the best of them. Then in the second round, it already computes 8 simulations. And so on. We keep increasing the trials until at one point, eventually we are going to have a hit. So far, however, we do not keep track of the current round. We add that in a second. Once the run simulations function we just discussed returns with the best shot out of a number of simulations, the computer can finally throw for real. Now with the simulation mode turned off, we initialize the bomb one last time and set its final velocity. We also show the final angle and velocity in the info panels. The wall simulation is nearly instant, but it's nicer if it looks like the computer has to think about it. We delay the throw by 1 second with the setTimeout method to make it look like the computer is thinking. In the meantime, for that 1 second, we call the draw function to draw an aiming gorilla. Later, we also update the look of the gorilla to show that the computer is thinking. Now, before we calculate the current round, let's add a new top-level variable, the number of players. If this value is 0, then the game will autoplay. 2 computer-controlled gorillas will fight each other. If the value is 1, then we have single-player mode. And finally, if the value of this variable is 2, then we have 2-player mode. The game behaves as it did before. In this tutorial, we consider the number of players as a constant. You can only change it from code. In the extended version of codepen, however, You can change this setting on the UI. Then let's add the missing round property to our state in the new game function. By putting it here, we also make sure that with every new game, it resets to 0. Now that we are here, we can also kick off the game in case the game is set to autoplay. In this case, instead of waiting for the player to grab the bomb and aim, the computer should throw the bomb. At the end of the new game function, we hand over the control to the computer and call the computer throw function. There are two more functions that we need to update to complete the computer logic. In the animate function, we increase the number of rounds. We only want to increase this number once both players had their turn. So we only increase it after we switch back to the first player. After a miss, we also need to check whose turn is it next. If it's the computer's turn, then we call the computer throw function. This can happen in two cases, either because the game is in autoplay mode, or because we play against the computer and it's the computer's turn. Here we add a little timeout to avoid a visual glitch. Before we update the gorilla and make it look like thinking, we need to change one more thing in the code. The simulation should not have any side effects. We simply need to know where each throw will end up to know how far we are from the enemy. However, when we hit a building, it logs the position of the impact, and that would eventually end up as a blast hole. We don't want that, so we modify this function to only log the position of the impact when we are not in a simulation mode. With this final piece, the simulation now should run properly. If we set the number of players to 1, you can play against the computer. When we play against the computer, it can be a bit confusing that the enemy gorilla looks the same as the player. To avoid this confusion, as a final finishing touch, we can create a variant of the gorilla that appears to be thinking. Let's add a new function call in the drawGorilla function. We add the call to a new drawGorilla thoughtBubbles function. This will draw a few question marks above the head of the gorilla when the computer is aiming. This function starts with two conditions. First of all, it only draws anything if we are in aiming phase. Then we have to check if the player the function is drawing is the current player and if it is a computer. In case it is, we can draw a few question marks with the fillText method. The fillText method has three parameters. The first one is the text itself, and the last two are its coordinates. We want it to be above the head of the gorilla, so we move it along the y-axis. There's a bit of complication here though. Because we flip the coordinate system, the text shows up upside down. To render the text properly, we need to flip it back, and now instead of moving the text by plus 90 units, along the y-axis, we need to move it by minus 90 units. We also apply a slight rotation to the secondary question marks before we draw them. With all this together, we finally finished our game. We can set the number of players to 0, sit back and watch two gorillas fight each other. While now we have a full game, there's always more to add. On codepen, you can find a version of this game where you can also select the number of players on the screen. In that version, the bomb is also affected by the wind to make the game more challenging, and it has support for dark mode. Here are a few more ideas to improve the game. What if you implement special bombs that take out a whole building, or that can cut through the buildings entirely? If you come up with your own version, don't forget to link it below in the comments. Thank you for watching. If you like this video, please subscribe as more JavaScript game tutorials are coming. Let me know in the comments below which game do you want to see next. See you at the next one.